Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. When you open a web browser, what do you type in as a URL? You type in an IP address or a name. Chances are really good that you type in a URL name like google.com, and that's because names are way easier to use, especially for us humans. Domain name system, or DNS, is a protocol that maps names to IP addresses. Before DNS was a thing, there were other networking naming protocols that existed. The only two that continue to work today are Microsoft's NetBIOS names and the host file. NetBIOS was developed by Microsoft in the 1980s, and it used broadcast for name resolution. Basically, a computer would boot up and then broadcast its name and its MAC address. Every system on the network could hear this broadcast, and they would cache that information. NetBIOS was only good for small networks because it provided no logical addressing like IP addresses. And second, broadcasting doesn't work well with large networks. As time went on, the state of NetBIOS wasn't practical, but it still served a purpose in Microsoft environments. With that in mind, Microsoft developed NetBT, or NetBIOS, over TCP/IP so that it could still be utilized. Unfortunately, NetBIOS only handles host names instead of dealing with DNS, so it ran into some issues with the SMB protocol for file sharing, which runs independently of NetBIOS on TCP port 445. NetBIOS over TCP/IP uses TCP ports 137 and 139 and UDP ports 137 and 138. The host file idea goes all the way back to the ARPANET, which was the predecessor to the internet. The host file stores IP addresses that are matched with a name. Originally, the host file was manually updated by the Stanford Research Institute on every system at 2 in the morning. Can you imagine that? Clearly, as networks grew, this wasn't practical anymore to store all those names, but believe it or not, the host file still exists on systems today. Locations of the host file are based on the operating system, but you can open it up with any text reader. You can see the location on the screen, and if you see a line in it that begins with a hashtag or a number symbol, then it's a comment and the system won't use that information, but you can still read it. If you work in cybersecurity, this file is definitely an area of concern, but that discussion's for another time. DNS, or Domain Name Service, is a service that was developed because as the original version of the internet, called ARPANET, began to grow in popularity, we needed a flexible naming system that works across different time zones and with different sizes of networks. And DNS fills that role quite nicely. DNS uses UDP port 53, and it can also use TCP port 53 for zone transfers and responses that are larger than 512 bytes. One of the key aspects of how DNS works is by using delegation. That means that you have multiple levels of servers that delegate responsibility to other servers, and that way they can handle the enormous amount of connected devices on the internet. DNS servers divide the work by using resolvers and name servers, which are called DNS servers. Now, resolvers query the name server with a name to get the IP address for that host. And then name servers hold the name and the IP DNS records in a database that we call a zone. On the screen, we have the different types of DNS servers that exist, but the key parts that you need to know about are DNS root servers, which are the top of the hierarchy, and they cover every name on the internet. These root servers delegate name resolution to more specific DNS systems. And then we have top-level domain servers, which are the step below root servers, and they handle the top-level domain, or the TLD names, like .com, .net, .edu, and lots more that you're probably starting to see now. All the TLDs are issued by the Internet Corporation of Assigned Names and Numbers, or ICANN. Authoritative name servers are domain-specific name servers that exist for each top-level domain and are delegated the responsibility for that TLD. DNS uses something called a hierarchical namespace. A good comparison is the file structure on your computer, where you have the root directory, like the C drive, and then subfolders beneath that. DNS uses fully qualified domain names, or FQDNs, to track systems, and these are essentially the full URL or name that you need to access a specific location. For example, google.com. In any domain name, you'll have a root, which has domains, and the domains can have subdomains, and the subdomains can have individual hosts called host names. On the screen, we have an example of a fake, fully qualified domain name on cybertrainingpro.com, and what each part represents. Below this, you'll see what a local DNS name might look like that doesn't need to be internet accessible. Notice this does have a root period at the end, but we don't typically need this on local names. The domain on this name is local, and development is the host name. When it comes to DNS, we know that there's three main players. Records, which attach a piece of data like an IP address to a name. We have zones, which are containers that hold all the records for a specific domain. We have name servers, which are software that responds to queries about DNS zones. Now, name servers will store information about their own zone, but they might also store copies of zones from other name servers. Again, we call these types of name servers authoritative name servers for one or more domains. Within a single domain, we might have multiple name servers, which means that we're going to have a primary name server and secondary name servers. DNS servers must communicate with each other to keep all the records up to date. If one server gets a new record, it's going to send updates to the other servers using a process called a zone transfer. Now, a standard DNS query, also called a forward lookup, looks to translate a fully qualified domain name into an IP address. Then we have reverse lookups, which perform the opposite of this, and they can take an IP address and locate the fully qualified domain name. So are you curious how the DNS process works? Let's say you first enter a website URL into a web browser. Your system will then check its local DNS resolver cache in memory to see if it already knows the location. If your system doesn't know about the location, it can check the local host file for entries, which is more efficient than querying remote servers. If the location is still unknown, your system can reach out to the DNS resolver with a recursive lookup request for the IP address matching the fully qualified domain name. Of course, this means that your system has to know which IP addresses belong to the DNS name server. Your system is going to get this information one of two ways. You can either go in and manually configure it, or you can use DHCP to assign the information. It's pretty common for your system to have 2 or more DNS name servers to contact, but it needs at least one to work. The DNS server checks its resolver cache for the entry. If there's no entry, the DNS server needs to perform an iterative lookup to find the answer. This means that the server asks the root server, which knows all the addresses of the top level domain name servers like .com, .org, and so on. The server then reaches out to the TLD servers. The TLD servers send your DNS server the IP address of the authoritative name server for that domain. Your server can then reach out to the authoritative name server and receives back the IP information. Now your DNS server can cache the information for later, and your browser knows where to go for that website that you were looking for. So if you're on a Windows computer and you want to see the DNS information for that system, you can open up a command prompt window and type ipconfig/all. That's going to give you all the information about your networking interfaces on that system. And then you'll have a section that's called DNS servers, and that will give the actual IP address for your DNS servers. You can also use the ipconfig/display DNS command, and that will show a little bit more about the DNS entries that your computer knows about. And then if you're on a Linux system, it doesn't really matter which version of Linux that you're on, but if you open up a terminal window and use the command cat etc/resolve.conf, and you look at this file, and you'll see your name servers on the Linux system as well. For DNS to work correctly, it uses different record types to store information. SOA, or the start of authority record, defines the primary name server in charge of the zone. NS, or name server records, point to the server that holds the records or the zone. These also help the name servers to know where to point the resolvers to find the authoritative name servers for a specific domain below them in the DNS hierarchy. A, or address records, are assigned to individual hosts, and they hold their IPv4 addresses. AAAA, or Quad A records, are the same as A records, except they hold the IPv6 addresses. They have 4 A's because IPv6 addresses are 4 times as long as IPv4 addresses. Make sure that you don't get confused by Quad A's in DNS with the security term AAA or AAA, which is authentication, authorization, and accounting. CNAME, or canonical name records, act like an alias, and they hold a fully qualified domain name instead of an IP address. Commands like host, nslookup, dig, and ping can be useful to inspect CNAME records. PTR, or pointer records, reverse the function of A or Quad A records. They use an IP address for their names, and they hold the fully qualified domain name of a host at that address. These are only found in reverse lookup zones. Pointer records can only point a single IP address to a single fully qualified domain name, which is different from A and Quad A records that can point to several fully qualified domain names. MX, or mail exchange records, are used by SMTP servers to determine where to send mail. These records hold a fully qualified domain name of the server that handles email for the domain. SRV, or service records, specify the location of services. These records look a little different than the rest of the records, but the key point for your exam is that they'll reference other services like Kerberos, LDAP, SIP, and many more. TXT or text records are a free-form type of record that can be used for just about anything. When it comes to the internet, there are several public DNS servers that you'll likely see used. These servers can help perform your internet DNS resolution. A huge issue with DNS in the early days was that entries needed to be manually updated. What a pain. Well, to solve that, dynamic DNS was developed. Now, dynamic DNS, or DDNS, was developed in 1997 to enable DNS servers to receive automatic updates of IP addresses of computers in their forward lookup zones by talking to the local DHCP server. In Windows environments, Active Directory uses DDNS to update their records. If you're on a Windows client that needs to have its records updated on the Active Directory DNS server, open up a command prompt window and type the command you see on the screen. If you can query a DNS server and retrieve every single computer name and IP address, well, that's a huge security concern. DNS Security Extensions, or DNSSEC, is an authorization and integrity protocol that's designed to prevent bad people from impersonating legitimate DNS servers. DNSSEC is implemented through Extensions Mechanisms for DNS, or eDNS, which is a specification that expands several parameter sizes but maintains backward compatibility with earlier DNS servers. Let's talk about some DNS troubleshooting. So if you have a server not found error, these are one of the first clues that DNS might be having problems. If you get this kind of error, perform these steps to troubleshoot it. The first step is to clear any DNS caches on the system. On a Windows system, open up a command prompt and type ipconfig /flush DNS. The next thing that you can do is use the ping tool and try pinging a fully qualified domain name like a website. When everything's working, you'll get an IP address associated to that name. It's okay if you get a request timed out message, but the IP address translation is important. Now try accessing a local server that you also know the IP address for. If the ping works, but accessing the fully qualified domain name doesn't, then you have a DNS problem. Correcting a DNS problem is usually pretty easy once you've identified it. On a Windows system, open up a command prompt and type ipconfig /all to see all the DNS name servers configured. If these aren't correct and you have the information automatically assigned from DHCP, then you need to go onto the server and correct those settings. If all the settings are correct, next try using the NSLookup tool in a terminal or a command prompt window by typing NSLookup the website URL or the IP address. And you can even add in a specific DNS server if you want on the end. If you get an error saying server not found, well, then the name server might be down. On Unix and Linux systems, you can also use the dig tool by typing dig -x the IP address in a terminal window. If your network interface card isn't working, you won't be able to communicate at all. If your DNS server is on another network, is your router working? It's important that you start at the simplest steps and you kind of work your way up the stack.